This is yttrium oxide. It's a rare earth element which has been bound with oxygen, from lasers to dental ceramics to fighter jets. And it's one of 7 rare earth elements which China this year has restricted the export of.
The majority of people pass a contaminated creek without giving it any thought. However, scientists discovered something in that contaminated water in some places of the United States that completely altered the situation.
With shovels in the ground, Ramaco opens the first new rare earth mine in the United States in over 70 years.
They found rare earth metals behind the orange streaks and strong odor.
Here they're drilling for the first time in a decade, going deep to learn more about the rare earths and critical minerals down below.
The same metals that run cell phones, electric vehicles, and cutting-edge weaponry. Additionally, China, the nation that controls the majority of the world's supply of rare earth elements, is not pleased about this.
From the other rare earth element mine, that this is in soft rock, it's shallow, it's easy to access, and the volume of it is simply gigantic.
And we will sell it to domestic customers, and that will be our answer to China.
The startling finding in U.S. rivers. If you had spent a few years strolling along Decker's Creek in northern West Virginia, the water would not have appeared suitable for swimming or fishing in the past. Locals recall sections of the stream being of vivid orange color, with brown and red-stained boulders and an overpowering smell of metal.
The purpose of this is to take the untreated mine water. The water will have a higher pH.
When the water comes right out of the mine into the creek, it's very acidic.
Parts of it were referred to as a cesspool rather than a stream. There were few insects and no fish. The first indication that something significant was occurring in the water was that peculiar hue. Up in the hills, abandoned coal mines were the source of the issue. Long walls of fractured stone with a glossy mineral known as pyrite were left behind when mining firms dug tunnels into the rock and then left. Because pyrite resembles gold but is worthless on its own, it is frequently referred to as fool's gold. A gradual reaction begins when air and rainfall gradually come into contact with that pyrite. A type of acid is produced by the mineral. Metals are then drawn out of the surrounding rock as the acid eats away at it. As a result, rusty acidic water, known as acid mine drainage, flows directly into neighboring rivers and creeks from abandoned mine entrances. Acid mine drainage affects more than simply the water's appearance. It makes living in the stream difficult or even impossible. Water continues to flow through the old tunnels and garbage piles, allowing the drainage to continue for decades after mines close. Acid mine drainage in Appalachia was viewed as a curse for many years. Along waterways that should have been a source of pride for the community, it damaged drinking water, rusted pipelines, and lowered property values.
The lime slurry pumps through these and goes to the chemical injection manhole where it's injected into the AMD.
It's like filling up a glass as the water, either through groundwater or direct infiltration.
When geologists and chemists began examining that same contaminated water more thoroughly, they discovered something unexpected. Iron and aluminum were not the only metals being torn out of the rock by the acid. Additionally, it was extracting a class of metals that most people are unaware of. However, that is what contemporary technology relies on. The rare earth elements are these.
Called pyrite and water. You get sulfuric acid and iron.
17 metals that are grouped together on the periodic table. They can be found in the small speakers found in phones and earbuds, the magnets found in wind turbines and electric car motors, and the guiding systems used in fighter jets and smart bombs. Researchers discovered that this contaminated water and the solids that emerge after treatment can contain rare earth levels comparable to some commercial or deposits in a lengthy study of coal mine drainage throughout the Appalachian Basin. Depending on the amount of water flowing and the strength of the drainage, a team of scientists working with the U.S. Geological Survey calculated that coal mine drainage outflows in this region carry between 1 million and several million pounds of rare earth elements and yttrium annually. They made note of that this range might be between a tenth and nearly half of the amount of rare earths used annually in the United States. The way these odd metals behave in various types of water explains why they accumulate in contaminated creeks. In acidic environments, rare earth elements typically remain dissolved and mobile. They're far more likely to be trapped in rock or soil in a typical clear stream with a neutral pH. Rare earths are more likely to separate from the rock and follow the flow in acid mine drainage due to the extremely low pH and high concentration of other dissolved metals. These metals may then sink to the bottom of the mud as the water enters treatment ponds or wetlands and the pH rises.
We process acid mine drainage. It's one of hundreds of plants around West Virginia where we're actually cleaning the water and we're putting it back in the river, restoring aquatic life.
A good illustration of how this manifests itself on the ground is Decker's Creek. The brook flows from the highlands of Preston County to the Monongahela River in Morgantown over a distance of just over 20 meters. Richard Mine is located directly upstream from Morgantown and is one of the worst mine runoff sites. There, a little creek receives a constant flow of unpleasant, low pH water from abandoned underground mine workings. Every minute of every day prior to treatment, that flow brought massive amounts of iron and other metals into Decker's Creek. As part of a larger initiative to resolve issues with abandoned mines, the state and federal governments, in collaboration with local organizations, eventually provided funding for a sizable treatment plant at the location. Since being online in the middle of the 2020s, the facility has helped trout and other delicate species begin to reappear while also preventing thousands of pounds of acidity and metals from entering Decker's Creek annually. When researchers from the Water Research Institute at West Virginia University, when they went to locations like Richard Mine, they observed something different instead of just the color and fragrance. They collected samples of the sludge that results from the treatment system, allowing metal to settle in a holding pond while adding lime to the acidic water. They tested the exact amount of rare earth metal in the damp orange sludge. According to the Institute, sludge from certain locations in southern West Virginia can contain almost 1.5 pounds of rare earth elements per ton of dry material. Sites in the state's northern region might get as much as 2 pounds per tons. These levels are on par with or higher than some hard rock rare earth mines found elsewhere. China and a few other foreign producers still provide the United States with nearly all of its rare earth supply, primarily in the form of completed goods. A strategic advantage that is just waiting to be developed is having a domestic source connected to former coal mines. The fact that other mining districts exhibit the same pattern makes this revelation more than just a West Virginia tale. Research conducted in western states, such as studies on water flowing from historic hard rock mines, also has elevated levels of rare earth elements, which migrate into solids when the water is neutralized, according to research on acid mine drainage near Idaho Springs, Colorado. Put another way, contaminated creeks and treatment ponds in a number of states are subtly functioning as a network of artificial or bodies that replenish themselves as long as mine water continues to flow. It's helpful to take a brief look at how rare earth metals are typically manufactured in order to understand why that matters. Large open pits or deep underground workings that unearth rock with very little usable metal are frequently the first steps in traditional rare earth mining. To extract each element, the ore must next be crushed, soaked in potent chemicals, and driven through numerous processes. Along the route, radioactive elements like thorium, which are found in the same rocks as rare earths, are frequently encountered by miners. These actions increase expenses, produce substantial garbage piles, and frequently stir intense local resistance, which is one of the reasons why a large portion of the mining and processing was eventually concentrated outside. On the other hand, river systems impacted by former coal and metal mines have already completed some of that work independently. The metals are dissolved by the natural chemistry in the abandoned tunnels and released as liquid into adjacent streams. Metals are already extracted from the water and concentrated into sludge by current treatment facilities, which were constructed to improve water quality. For someone searching for rare earths, this indicates that the expensive initial stages of excavation crushing, and initial separation have already been completed without the need for more drilling or blasting. The fetus is laying there like a damp, metal-rich muck that needs to be cleaned up in order to maintain clean streams. Finding hidden metals in river muck is one thing. Converting those discoveries into a consistent supply of high-purity material that manufacturers and defense suppliers can truly put to use. This challenge shifts the narrative from river chemistry to full-scale engineering, where the actual process of converting trash into a new resource starts. How the U.S. turns hazardous sludge into valuable metals. The mining water enters huge mixing tanks in a treatment facility. Lime, a typical alkaline substance, is added by workers as a white powder. Lime reduces the acidity and softens the water. Many dissolved metals begin to transform into tiny solid particles at that point. These particles start to sink because they are heavier than water. After that, the water enters tall, circular tanks known as clarifiers, where the cleaner water spills over the top and continues while the heavier particles sink to the bottom as sludge. The team at West Virginia University went beyond the antiquated one-step method. They discovered that the metals may be separated out in a method that greatly facilitates the collection of rare earths by passing the water through a two-step pH process. They elevate the pH to about 4.5 in the first phase. Many iron and aluminum particles fall out of the water at that level and settle into sludge, but the majority of the rare earth elements remain dissolved. The pH is raised to about 8.5 in the second phase. At that point, the rare earths and a few other precious metals like cobalt and zinc eventually disappear. They may extract a thicker, heavier sludge that contains significantly more rare earth metals than the typical waste from an old mine by splitting the treatment process into two stages. The new strategy is evident at Richard Mine in the layout and construction of the entire facility. The cleanup procedure was divided into two distinct routes by the engineers. Thus, the rare earth-rich sludge travels in one direction, while the typical sludge from routine water treatment travels in another. They take great care to protect that unique earth stream. This heavier mixture is pumped by the plant into Juexal bags, which are long, white cloth tubes that are spread out in a different area of the site. These bags function as enormous filters. A thick, heavy sludge is left behind as water gradually seeps out through the cloth. According to tests, this mud can contain between 1% and 2% of rare earth metals by weight once it dries, compared to the minuscule trace quantities that were floating in the initial water. That represents a significant increase. To put it simply, the plant transforms an unpleasant orange soup into something far more useful. A pre-concentrate of rare earth metals that is small, portable, and transferable to the next link in the chain. The National Research Center for Coal and Energy at West Virginia University's Rare Earth Extraction Facility in Morgantown receives that pre-concentrate. In order to determine if rare earths from waste streams, such as acid mine drainage, may be converted into a reliable domestic source, the U.S. Department of Energy funded this pilot facility. It appears less like a college structure and more like a small industrial plant. Tanks, pumps, steel platforms, and lengthy frames with day and night operating mixer units. The engineers must first turn the metals back into a liquid. However, they must regulate how that takes place. In heated tanks, workers combine the dried sludge from Richard Mine with a mild acid, typically hydrochloric acid or a comparable substance. Rare earths and other metals are drawn from the solid and into the liquid by the acid. Grease is removed from a pan using warm, soapy water. After completing this stage, they have a robust liquid mixture that contains all of the metals that emerge from the sludge, containing the iron, aluminum, and other metals they do not want, as well as the rare earth elements they do. Solvent extraction is the next step in the actual sorting process. Although the nomenclature seems complicated, the fundamental concept is straightforward. Water and oil do not mix when they are poured into the same glass. One floats atop the other. All of the metals are contained in a single water-based liquid in the pilot plant. The other is a liquid that resembles oil and has been adjusted to absorb rare earth elements while disregarding the majority of undesirable metals. The vegetation passes both liquids through a lengthy row of settling and mixing tanks. To allow the rare earths to migrate into the oil-like liquid, the workers mix the two liquids in each tank. After that, they let everything to settle until the liquids once more separated into two layers. They keep doing that. The majority of rare earth metals have entered the oil-based stream after numerous phases. The plant does another flip once the rare earths are securely contained within that organic liquid. The rare earths are extracted back into the water by washing that liquid with a pure acidic solution. However, they are much purer now than they were. What's left over when the engineers finish the last chemical processes and evaporate the water is a powder known as rare earth oxide. Magnet, battery, and alloy manufacturers purchase these powders on the open market. Small batches of mixed rare earth oxide powders with purity levels of about 98% by weight have previously been generated by early pilot systems such as this one. That level of purity is sufficient to demonstrate that this process can produce actual commercial stuff rather than only lab samples. Researchers from West Virginia University collected samples of acid mine drainage sludge from coal country and showed each metric ton of dry sludge at some locations in southern West Virginia contained roughly 666 G of rare earth elements. Sites in northern West Virginia attained about 750 G per metric ton. To put it simply, that is about 1/12 to 1. For every short ton of garbage, there are 7 pounds of rare earth metals. Although the figures may seem insignificant, they are comparable to or even superior to some ore deposits that are mined in open pits in other nations. The percentage of heavy rare earths in these sludges can occasionally be particularly high.